better. It's good to start having that feeling.
I still have the dry cough.
Oh, I'm sorry.
Oh, see, this is what my sister does. She said
Yesterday, I got tested for COVID and strep, and I came back negative.
I'm glad they both came back
They said
negative.
that it's probably just side effects from the second shot.
Are there any Chem 1020 related questions?
Maybe do like a 10 question stuff after every chapter, maybe.
A 10 question stuff after every
Like, so like we go over like math equations.
Okay.
Right? Could you post like examples of those online too, so that we could practice some more after, like I say, every lecture that we do maths related stuff.
Okay. What I'm going to do is I'll actually do some of that right here now, just to highlight where we've been and what we've done so far. And then I'll try to remember that again, maybe in another day or two. I don't know if I'll have the resources to post a separate document, but that's why I went and posted all the answers to the end of chapter questions. So you can kind of go through the end of each chapter and look for additional problems if you want to practice a particular type of conversion or relationship. But let's do a couple of those right now. So switch over here. So looking at the big picture, we can relate any two chemical quantities using a balanced equation. And we can get into and out of moles a couple of different ways. Our focus right now in the third unit are looking at relationships involving mass or molarity. And we haven't talked about molarity explicitly here, but we're going to turn around and do that later today after I get a chance to kind of highlight where we've been so far. We have, however, addressed molarity repeatedly in lab, particularly the determination of bleach concentration, determination of vitamin C content in the packets. So we have used molarity, but I want to bring it back and go over it again. Later in the semester, unit 4, we'll deal with gases and what to do about energy. But all of these depend on the number of particles. That's the central feature. So as you look at any question, and this gets back to the review kind of piece that you were looking at, any question on exam 3 or exam 4 is going to involve this central assessment on your part. Am I asking you about one substance and asking you to describe the substance in a different way? Or am I saying, hey, I've got information about this one substance and I need to know about this other substance? That's it. Every single question in exam 3 and 4 falls into one of those two categories. Am I asking you about one substance and asking you to describe it differently? So I give you a mass and ask you to work out a molarity, or I give you a volume for gases and I ask you to figure out how many grams that would represent. Or am I saying, hey, there's this chemical reaction and I've got so much of this stuff and I want to know how much of the other stuff. Now, a subset of that is, okay, I've got this reaction and I've got information about both reactants. How much of the product can I make? Now, it's the same idea. You've got information about one thing and you're trying to figure out how much of the other thing, but you've got this confounding issue of you don't know which of the ingredients is going to slow you up, which of the ingredients is going to cause you to run out. But that's it. And particularly in the third exam, that's especially important. Or am I asking about one chemical substance, or am I asking you to take one chemical substance and figure out a second chemical substance? So just a quick reminder, one substance or two. That should be kind of the first question that pops in your head as you look at any question I ask you. So then so far what we've done is we've looked at this mass to moles relationship. And that's coming in a couple different ways. We've talked about percent composition. We've talked about empirical formulas. And underlying both of these guys is how do you get from grams to moles? And how do you get from moles to grams? So if I were to begin a list of sample problems that you have to be able to do, I would start off by saying, hey, if I've got 2.5 moles of sodium carbonate, how many grams is that? Or if I've got 115 grams of calcium nitrate, how many moles is that? Or if I've got C2H6O, what's the percent composition of each element? Or let me see, sorry, let me crunch the numbers here real quick. So something 62.1% carbon by mass. And it's 10.3% hydrogen by mass. And it's 27.6% oxygen by mass. What's its empirical formula? Now, Isabel, I hate to put you on the spot, but you asked a really good question or made a request I thought was pretty reasonable. This is what I heard from you. Is this the kind of that's kind of what you're talking about?
Yeah.
Like kind of calculations? Yeah, you have to do, these are all things that would show up on the exam. I'm trying to communicate that to you as concretely as possible. And you should start looking at the practice exam. And the reality is there's not very much new that we have to go over. When I see you on Thursday, we'll get into the details of the types of reactions that are out there. Precipitation reactions, acid-base reactions, reduction oxidation reactions. But as far as all the calculations, you've actually already done all the calculations we're going to be doing in lab. That doesn't mean you're supposed to be experts at it. I'm just saying there's no new material. I'm just trying to get you more familiar, particularly with the concept of molarity. But in terms of what we've covered so far, you have to be able to get from moles to grams. You have to be able to get from grams to moles. You have to tell me what the percent composition is for any particular formula. You have to turn that back around and say, if you know what the percent composition is, what's the ratio of how many atoms of each element are present in the compound? And if you notice in each of these, I'm only asking you about one substance. I'm asking you about the sodium carbonate. I'm asking you about the calcium nitrate. I'm asking you about the C2H6. There is no chemical equation. We're not trying to get from moles of one thing to moles of another. That's the key in all of these calculations. So what I'm going to do is give you about 5 minutes. I want you to work these 4 problems out. Talk to your neighbors. Make sure you can explain what you've done to a neighbor. Make sure that neighbor can explain what they've done to you. And while you do that, I forgot those papers I want to pass back, so I'm going to grab those.
Add up the weights and everything, and then, yeah. So like here, like, really that grand.
2.5 moles of sodium by carbon. What's my cursor? It's a low leaf, whatever.
Did you do the?
Yeah, and you too. I mean, okay, okay. I don't know where you got the 4. Oh, you subtracted CA. There's 16 minus 12, 4. So there's 400. Each 4, yeah. And then you just divide it by the amount that there actually is. Yeah. And then times by 100. Okay. I've done all those. Yeah.
The rocks.
I told you that. I was like Friday, and I was like, oh shoot.
Better late than ever.
64 grams.
My sort of carbon. Is that what you were wanting for that?
That was perfect.
Okay,
Yes.
I didn't understand. If you want to keep it, you can have it.
I'm actually quite, I will take it.
Because it will honestly end up in the trash.
What? This goes on the fridge. How does this not go on the fridge?
I don't have a fridge.
You don't have a fridge? Not even like a little, even like a little one?
Not that I posted one. No, the fridge at home's for Christmas cards.
Oh, I got you. Okay, yeah, I get that.
The total value is 3046.
Sorry, I'll put it back up here in a second. I do want to thank you. Those of you who got your carbon story in, I sure appreciate it. There's one right here apparently, which is not going to go on a refrigerator. So I wanted to make sure I shared some with you.
Oh, wow.
Yeah, I know that.
Way better than-
I know. I thought this was pretty cool. Sorry, didn't I not say it's better than yours, Ben? But
Wait, what is that?
oh, I like that rock. That's a cool rock. And that's, tell me that's not a cool looking fireplace. That's pretty awesome. Falcon. And then, oh, look at the detail on the leaves. A little ins and outs, nooks and crannies. And that brain, that's clear. I mean, I don't even need the caption. I know that's a brain right there, or maybe a piece of cauliflower, but it's pretty cool. Back in the human body.
Weird. I had a good idea to write a card.
Thank you for that, Nicole.
Yeah, you can keep it. I just found it.
I will. I'll give you another minute or so and I'll start putting some answers together. I'm asking you to be as aware of your problem solving as possible. If you're running into a difficulty, try to write out in words, what is your difficulty? And I'm going to come to that here in just a second.
I got.
This, so look.
Once you get from hard, you get
This
52.
is what we use.
Okay, that's fine.
C2H6 with equal 1. So we find the mass of that, and then we take a mass times.
Right now, I'm hearing a couple different conversations that are really encouraging to me, people that are checking in with neighbors. If you're at an impasse on something, just call me over. We're gonna add a couple minutes to this because it's really important for us to get these fundamentals down. Not sure about something, start by turning to a neighbor. Ma'am? About something that can help you all out at once.
Not yet. I was trying to remember.
Shouldn't assume. It's 48. This is the first two.
What is that word?
Calcium.
My eyes were just messing with me. I'm pretty sure.
No, I think it's my hand. I think it's my handwriting.
That is 100.
Thank you.
Okay, wait, sorry.
Isn't it like this? Yeah. So you escape first.
I just got a really small number. Oh, wait, so if you're divided by the molar mass,
Mr. Norman, so when you do that, if you go to say verbal formula, so you calculate the percentage. And then you assume 100% composition, and then you put that moles, so it's carbon, and you determine all fractions, right?
So actually, you're coming around full circle. So
Oh, wait.
percent composition is just stop.
Just H6.
That formula.
Oh, and you want the empirical formula of that one? Oh, I figured.
So yeah, so that's a
Oh.
separate problem. Yeah.
Oh, okay, okay, that would.
So what would have happened is if you divide through by the smallest number.
Okay.
but it would be times.
Okay, so why do you put it over 12?
Oh, wait, no, it's not 7, that's percent.
Percent
Why I
composition.
put over 12? Because there's 12 grams more today.
Oh.
I'm trying to get it in.
That was-
Did you get to this part? Yes. Okay. Oh, so Nelson.
I'm seeing you guys on Friday morning.
So these are the other two plus
This one, this one is melting. Yes, that
I just did it in 5 minutes.
that was, sorry. Not that there's
That's
anything wrong with that. but This is more frigid. That right there is definitely, these two right here, that's frigid.
And that's what I tried.
You're gonna add one.
Yeah.
That's how you did percentage. I still clicked the part divided by the whole.
Why can't I
So
get?
I want you to continue to work. I'll start putting answers up here.
And
You can
then
kind of check your work.
figure out what percent each element makes.
Wait, what did he say? If when you divided it, you had decimal form? Do you remember?
So that's also
you-
because what
it's like when you get the empirical formula.
because that was different. That was that was me doing the last one.
Yeah, but so I divided that by that because it's the smallest one, but I'm not getting.
This 46 is custom.
I'm not.
24 by that.
I did it in a very bad way, but
Okay, so now you need to divide by 1.7.
so I divided that, but I'm getting a decimal, so I don't know.
Oh, but it's 5.97. It's. The only decimals we need to worry about are things that are not near a whole number, so like 0.5
Okay,
or 0.75 or 0.25.
Okay.
But if it's 0.987 or 0.01, 0.02, that's pretty much a whole number.
Yep. So we're trying to figure out what percent of this mass each one is. For the third one.
4.7. Going down to
Electrons.
Just kind of the same thing. Like if you, because if you added all these, up, you know what it has to be. And then moving forward, it's just, if you have these and you know you have 6 items, then other way around. Get 6 items. One off shit, yeah. Like,
So actually, I'm
So,
gonna show you mine, 'cause it's a joke.
I just added until it
Okay.
the two. The last one.
Yeah, no, it's not. And I got one.
Really, I enjoy it like that's like a thing that I'm like, I can do this design.
Okay, are there any questions on the first two? Should have 265 grams of sodium carbonate
Yes.
or 0.7 moles of calcium nitrate.
It's okay. He's doing it.
So you have to make it to the space.
So for that first one,
So first you have to figure out the ratio of sodium to
that's why. Okay, wait, that actually makes
carbonate.
This should.
It's literally just yeah, so we had to figure out that. And then figure out the grams per mole.
Okay, so for the third one, 52.2% carbon, 13% hydrogen, 34.8% oxygen. If you and the people you're working with are having trouble with that, take a little break and I'll come over and catch up with you individually. Just let me know where you're at.
And then who's back? Because I read this all.
You have it. Where you know you're wearing the avatar, are you going to like, you just like.
It's actually a nice thing.
Well, gassed up. You found the molecular mass of C2H6. What do you see on it? 64.
C3H6.
Dr. Miller,
On the question for 115,
Yeah.
underneath the 1 mole, is that 104?
That's 164.
Okay.
That's so cute.
Yeah.
Those are like gay guys.
Okay, so the empirical formula for the final problem is C3H60. That is the simplest whole number ratio. You would not be able to decide if that's the molecular formula without additional information, specifically the molecular weight. I'd have to give you the molecular weight and say, hey, the molecular weight for this stuff is 56 grams per mole. And then you'd say, oh, that's the right number.
I see.
Sorry, 48. No, sorry, 36 plus 6 plus 16. Sorry, 58 grams per mole. If the molecular weight were 116, you'd know you'd have to double that number. So you'd have to have C6H12O2 if it was a bigger molecular weight. So that's where we're at officially in lecture, coming through chapter 6, getting ready to move into chapter 7. That's officially where we're at. Those are all the problems I'm expecting you to do. So if you need additional practice on any of these, go to the end of chapter 6 and look for a full section that has these calculations in it. And then look for the answers for the even problems available through Canvas. You can always send me pictures of your works. If you're working on a problem and you're not sure if it's right, just take a picture, email it to me. I'll be happy to tell you whether you're on the right track or not. Yeah.
Quick question, why would the oxygen be 0 or 1 instead of 2 if the 7's higher than 5? Do we round up at all on that?
So as provided here, we divide through by the smallest number. So we end up with 1 oxygen.
Oh, so you divide it by that number.
Right. So if you divide by the 1.725, you get this ratio of
You just
1.
get 1. Okay, that makes sense.
Without knowing the molecular weight, we go with the simplest whole number ratio. That is the empirical formula. If I told you that the molecule actually has a molecular weight of 116 grams per mole, you'd have to double this ratio. You'd end up with C6H12O2 at that point.
Okay, thank you.
Other questions? So the other major way that we get into and out of moles for dealing with chemical substances has to do with the fact that most of the time, a lot of the time, we're working with solutions. That has to do with the nature of our planet, the fact that we've got so much water here. There are several different units for describing concentration. Molarity is only one of them. But for chemists, it's a really important one because it relates to important quantities. Specifically, it relates the number of moles, which we use for counting particles, to the number of liters, which we use for describing volume. And those are two quantities that we can measure reasonably easily. Moles we can measure directly if we can get the substance as a solid. We can then weigh it out and know how many moles we're dealing with. And volume, liters, is relatively easy for us to agree on based on the glassware that we have available to us. So molarity is a really useful ratio. It really is, in a sense, a conversion factor. It's telling you how many particles there are dissolved in a particular volume of solution. Now, molarity can be rearranged in a couple different ways. We could solve for the number of moles. That's molarity times liters. Or we could solve for the volume of solution. That's the number of particles, moles, divided by the molarity. Now, it's up to you. You can memorize all three or just memorize the one and do the algebra. My preference, of course, is memorizing the one and doing the algebra. But I like algebra, and that's a quirky little thing about me. I enjoy it. You decide which one you want to do, but you have to be able to do all three. And so anytime we're dealing with a solution, and the question will say, hey, you're working with a solution of calcium nitrate, you're immediately on alert for which of the three do I know? If I know the moles and the liters, then I'm figuring out the molarity. If I know the moles and the molarity, I'm figuring out the volume. If I know the molarity and the liters, then I'm figuring out the moles. If I've got, going back to that fundamental question, am I dealing with one substance or two substances? If it's two substances and you know you've got this solution and you're reacting it with another solution, you know you're gonna have to get into moles. You know it's gonna be this one over here. If you're trying to get into moles for solutions, this is your go-to relationship. Now, I know this may not look familiar to you, but you've used it twice already. You used it in the bleach lab and you used it in the vitamin C lab. So you've used the relationship, but now what I'm telling you is you have to know it and be familiar with it. If you want to figure out how many moles are in a solution, you take the molarity times the number of liters. So let's do a couple practice problems. This is from page 232 in your textbook. This is question number 100. We'll look at part B. How many moles of solute are present in each of the following solutions? We got 175 milliliters of 0.67 molar glucose. How many moles of solute are present in that solution? I'll give you a 30-second head start to see what you can work out. Oops, let me put the problem back up. So here I've rewritten the problem. 175 milliliters, 0.67 molar glucose. Molarity equals moles over liters. Here I have a quantity I can turn into a volume. That's liters. Here I have the molarity. The only thing I don't know, the only question mark is how many moles are present. So we go through the problem and identify what information do we have and try to figure out how is this relationship going to get us to that unknown quantity. In this case, we're trying to figure out the number of moles. So I've got to multiply by liters on both sides. Moles equals molarity times liters, which equals 0.67 molar times 0.175 liters. Remember, to get from milliliters to liters, you got to move the decimal point 3 times. Now I'm going to recopy this because that 0.67, I could rewrite the capital M as moles per liter. That's what the capital M means. Molarity is the same as moles per liter. The downside to moles per liter is it takes longer to write out. So a lot of times we'll write the capital M just because it's faster. But you have to recognize that the capital M represents a ratio. It represents how much of this to how much of that, specifically how many moles to how many liters. The reason why that's helpful is because when you multiply by a volume, the liters cancel out and the only unit you have left over is moles. So from a unit perspective, it actually makes a little bit more sense to take the extra time and write moles per liter to remind yourself it's a ratio of how many particles to how many liters. If you multiply by the number of liters, it tells you how many particles are swimming around in that solution. So I take 0.67 times 0.175. That's 0.117 moles. Now, at this point, we could go back to what we just talked about doing the review problems. And I could add to this question, okay, now you know how many moles there are. How many grams are there? Well, 0.117 moles of C6H12O6. I go to the periodic table, it's 180 grams per mole for this stuff. 0.117 times 180. There are 21.1 grams of C6H12O6 in there. So the moles ties us to mass. Not only do we get a sense of how many particles are in the solution, but we can tell you how heavy those particles are in the solution. Now, by itself, that particular piece of information would only be helpful if you needed to evaporate all the water and just have the solid left over. But from our perspective in chapter 6 and 7, it's just this idea of recognizing that moles are central to all of our calculations. That once we know the number of particles, we can go to how heavy the particles are. We can go to how they're going to spread out in a solution. If we were to get this stuff in the gas state, it can tell us information about what volume the gas is going to occupy under certain conditions. Questions?
Because it's different.
All right, let's try another one. This is question number 104. Sterile saline used to rinse contact lenses can be made by dissolving 400 milligrams of sodium chloride in sterile water, diluting it to 100 milliliters. What is the molarity of that solution? I was going to delete what I had on the board. Was there anybody who needed stuff from the board? 400 milligrams of sodium chloride, diluted to 100 milliliters. What's the molarity of the solution? I have recopied the problem on the whiteboard. Yes, I should say. 400 milligrams of sodium chloride in 100 milliliters. What's the molarity? That's just point. We're trying to find molarity. It's moles per liter. We're given the volume, So we've got that. That's pretty straightforward. We've got the number of grams we can get to moles using the periodic table. So we have both pieces of information, but they both need a little converting before we get there. Volume, we moved the decimal point 3 times. We got 0.1 liters. 400 milligrams, we moved the decimal point 3 times. That gets us 0.4 grams. And here come those calculations that we just practiced. 1 mole of sodium chloride goes on top, 58 grams goes on the bottom. That's coming from the periodic table. So it's a pretty small number of moles, 0.4 divided by 58. 0.0069. Divide by 0.1, that's 0.069 moles per liter. Or we could write 0.069 capital M, 0.069 molar. Again, one substance. We're not trying to use a chemical equation to get to some other substance. We're just doing one substance at a time. Questions? Yeah.
So like with chloride specifically, or the chlorine part of this equation, since it's 35.45.
Yeah, I know.
I'll have to round that down anyways.
Darn that chlorine. For our purposes, I'm asking round to the nearest whole number.
Okay.
So officially it's 35.4. So we'll round it down. Yeah. Right in the, it's one of the only ones that's right in the middle. It's the only common one that we run into is right in the middle. Everything else is like a 1/10 or 2/10 off of a whole number. So yeah. If there were a calculation error that cost you points on the exam because of chlorine, you just come and see me. Like if you rounded 30, if you rounded up to 36, I try to make sure the multiple choice answers are far enough apart that we don't have to worry about that. But if chlorine causes you grief, you let me know and we'll get it straightened out. All right, so now let's try a second substance. Now, I will mention that there's a lab later in the semester that this question will help you out with. I'll tell you more than that. Just as we get to that lab, you might see yourself, wow, wasn't there a question we did in lecture that might help us out with that? Oh, yeah. Copper reacts with nitric acid according to the following equation. 3 coppers plus 8 nitric acids make 3 copper nitrates, 2 nitrogen monoxides, and 4 waters. If a copper penny weighing 3.04 grams, 3.045 grams is dissolved in some nitric acid, resulting solution diluted to a volume of 50 milliliters, what is the resulting molarity of the copper nitrate? Here we've got 2 substances. We've got the metallic copper, and we're asked about the solution of copper nitrate we're about to make. We've got to go from moles of one thing to moles of another using the balanced equation. The question becomes, how do we get into moles and how do we get out of moles? So I'm going to give you a minute to try to struggle with this. At this point, I would call it a struggle because we haven't done a calculation involving 2 substances in lecture. You've done a bunch of these in lab.
Yeah.
How do you get into moles? How do you use the balanced equation to get to moles, the other thing? And how do you get back out of moles to describe the copper nitrate?
When is our next lab?
Sorry, next lab.
Yeah.
So if you guys met with me for HPLC last week, so you don't have to come on Thursday. I'll see you next Thursday.
Okay.
And it is, I think it's kind of funny. We go from using really high tech piece of equipment that I'm super excited to share with you. And your next piece of equipment is a styrofoam cup.
Oh.
And it's actually it's quite old and beat up, but it works. It does what it needs to do. We're going to look at energy changes and reactions.
Gotcha.
So you don't have, your group doesn't have to meet with me this Thursday. I won't see you till next Thursday for lecture, but I'll see you this Thursday for lecture. Then you just take off. You don't have to come back. Let's hear it. Yeah, so if I did not meet with your group to run the HPLC last Thursday, make sure your group signs up for a slot on that announcement that I sent out. So I know what time you're coming in this Thursday.
Are you gonna go over in class how to figure out the amount of like caffeine in our drinks?
Yeah, we can't actually do that until this Thursday because we won't have all the data until this Thursday.
Gotcha.
Yeah, but yes. So when I see you next Tuesday, I'm happy to do that.
Okay, sweet. Thank you.
So when I say, good morning, are there any questions? Isabel will ask how I'm doing. And then, then you'll say, then she'll say, then you'll say, hey, can you help me with the caffeine concentration?
All right, I'm talking
Oh,
about,
no, that's
talking about how I made a horse say moo to my little brother.
That's impressive.
Yeah,
Right, because they have the same ratio, so
Yeah,
it's
like
like.
an actual horse?
like, yeah, so we were listening to what does a fox say? And we passed by horses and I was like, look, Jack, what does the cow say? Moo. And
But the horse didn't actually say.
correct,
Okay.
but I made it.
That sounds much less impressive than the way you described it initially.
I feel like if you raise a horse with cows, it would eventually.
That is an interesting question.
Biology.
That is an interesting biology question.
You chemically engineer the cow.
Let's actually be genetically engineered.
Did you
Yeah.
get 0.966? I'm trying to do chemistry.
Thank you.
Wait, but they have the same ratio, right? So they're the same molar. I don't know.
All right, so I've recopied the problem in its essence here. We've got a 3 gram penny. We're going to react it with nitric acid, figure out what the concentration of copper nitrate is. So sketching this out for us, we're going to have to get to moles of copper. And then we're going to use a balanced equation to get to moles of copper nitrate. And then we're going to use the concept of molarity to get back to a concentration. So we have to get into moles, between moles, out of moles.
So will we use 3 moles or no?
Yep.
Yeah.
Yeah, it's essentially a 1-to-1 relationship. Every copper gets us 1 copper nitrate. Now, if you want to use 3 to 3, that's perfectly okay, but you're going to get the same answer. So just writing out our conversion factors before we actually get out the calculator. I'm not sure if that's correct. For every 1 mole of copper, it's going to weigh 64 grams. Every 3 moles of copper will get us 3 moles of copper nitrate. And then molarity is the number of moles divided by the number of liters. So those are the 3 relationships that we're going to take advantage of. We want to get into moles. So 1 mole of copper goes on top, 64 grams goes on the bottom. Told we're going to get 3 moles of copper nitrate. For every 3 moles of copper that we start with. Now here's the catch. There's not a good conversion factor set up. It feels kind of awkward. So what I'm going to do is erase this last conversion factor and just work out the number of moles at that point. So this is how many moles of copper nitrate we have. So 3.045. divided by 64 times 3 divided by 3. Got 0.0476 moles of copper nitrate. Molarity equals moles divided by liters. We've worked out that you're going to make 0.0476 moles of copper nitrate. And you're adding enough water to get it to 50 milliliters, 0.05 liters. Works out to about 0.95 moles per liter. 200. So the catch is this: the last step where we normally come out by using a conversion factor, especially if we're dealing with grams, there's not a clean looking way to set that up. We could, and I'll copy, you don't have to copy this over. I'm just writing it out as an example. I'm just rewriting the whole thing. It would be perfectly correct mathematically to say, you know what? I know that this answer of moles of copper nitrate, I'm just going to divide it by the volume. So all I do is I divide by 0.05 liters at that point. Oh, sorry, I got to clear this out here.
I think most of those. Just 188. 60. It's just over one. So it's
I get the same answer. The benefit here is that it kind of keeps our conversion factor structure going, but it doesn't matter which way you do it. I actually prefer for molarity to actually write the molarity equation out separately. Questions on how I set that one up? Let's have you try that again. This is question number 107. Well, it's the same idea. Pennies minted after 1982 have more zinc in them. So if a penny has 2.48 grams of zinc, and the final solution is diluted to 250 milliliters, what is the molarity of the zinc solution? This is question number 107.
That's pretty close.
So you have to go to moles of zinc. Moles of zinc, you're going to go to moles of zinc nitrate. From zinc nitrate, you're going to go to a description of the concentration to give you the volume of solution.
It was just introduced. Because it was percentage.
Oh, but now we have a percentage.
It is a 1-to-1 whole ratio.
Yeah.
Think about the percentage.
Worrying about that, we're worrying about zinc and then.
Oh, yeah, we do because the penny weighs that much. Oh, wait, we can do this.
Your ratio there. What is your ratio of zinc to zinc nitrate?
Oh, there's a percentage of zinc that we're trying to look for, so you can percent to find how much the zinc weighs.
That's how you're looking at zinc and zinc nitrate.
Well, I'm gonna go home and take a fat nap. This is the most I've been awake for the past 4 days.
Just do. And then you
I've been
can
taking naps like every hour.
just divide by this.
Like it's been rough.
No, I got 1.5.
What did you not, what'd you get? What'd you get?
Like I'm really just in lazy bed.
1.5.
And how like
Oh, okay, that must have been just like me not using a decimal.
there's more people that are like dying in hospitals still from it. It's crazy.
It's awful.
And with how they're blaming Trump Scott, I'm like, yeah, he saw it, but like, what is he supposed to do?
Well, there's something
You
just
still
different.
don't know where they have like personal boundaries. Stepping on people.
Don't you pick the rainbow and help them up.
Especially. Why would anyone under the age of 16 at the least?
So we don't have black.
The reason why it says.
Like, other than like, a 10-year-old should not be there. If anything, you should have been like go back.
Is what the zinc minus.
Oh, a 9-year-old just died.
Like the oldest one I know is like.
All right.
5%?
Scary.
So we take the grams of zinc, figure out the moles of zinc. This again is a 1-to-1 relationship. A lot of chemical reactions are 1-to-1 relationships. 0.038 moles of zinc nitrate get produced. That's swimming around in a total volume of 0.25 liters. Works out to a concentration of 0.153 moles per liter.
153 to 152.
Questions?
How do you say it?
So like each question on third exam, is there one substance and you're just going from mass to moles to molarity, just talking about the one substance? Or are there two substances and you have to get into moles, between moles and out of moles? That question?
Still chapter 6.
So this is still chapter 6.
Okay.
We're just about to move over to chapter 7 to look at the types of reactions. And so actually I'm going to do that. I'm going to transition here right now. So chapter 6 looks at the basic calculations of getting into moles, between moles, out of moles. Chapter 7 focuses specifically on the actual equation itself. If you've got two substances, what are the different ways atoms and ions can rearrange to come up with new combinations? So what I want to do is take the time we have remaining, give you an orientation to the types of reactions, and then when we get back together on Thursday, we'll go into each of the types in more detail.
What was the answer for the last one?
Whoops. 0.153 moles per
Because I
liter.
don't like my last name, so I did my little
Okay, they
Yeah,
explain-
yeah.
they try to explain, but why do you not need to multiply it by the percentage and zinc?
By which percentage?
rate.
Oh, that is mostly zinc. The only way you need to use that percentage is if they actually gave you the mass of zinc in the penny. They actually said the penny has 2.4. Oh,
I thought it
wait,
just said it weighs that much.
Yeah.
you're absolutely right.
Well, the thing is that in the
Thank
thing
you.
it says after the copper has got rid layer.
Yeah, it says after and then it says post.
Yeah.
Yeah,
But why would
And then
they
they
throw
don't-
that
That's what
at
I
you?
thought, like.
I believe, I think I'm standing by my decision.
No, Morgan, you are absolutely right. The way it is worded,
Did you hear that, guys?
the penny, and now I'm bringing in some external knowledge. I happen to know that when you weigh a post 82 penny, it always comes out at just about 2.5 grams. So what they've given you here is the weight of the overall penny. I misread the problem, that in fact, you don't have 2.482 grams of zinc. You have 97.5% of that. So you actually should take 0.975, 97.5% of 2.482. You have 2.42 grams of zinc.
So instead of point.
Should be 2.42 grams of zinc. Now, what that means is 2.42 divided by 65 times 1 divided by 1. That works out to 0.037 moles of the zinc nitrate divided by 0.25 works out to 0.149 moles per liter. All right, Morgan, well done. Yeah. All right, questions about that clarification, getting that straightened out? Okay.
It's so sad. Once you get over it, you watch it. It's so sad. Yeah, I mean, not to mention that we already were crying over our. That we both like won't be here next semester, and we're just like.
All right, so I'm gonna move on to types of chemical reactions. We good? Those are types of bonds. Those are types, we're gonna move on to types of chemical reactions. So how are those bonds rearranged? No, that is a rhetorical question. I'm gonna highlight the three types.
The cool one, the not so cool one, the boring one.
No, they're all cool. None of them are boring. Some of them are less dramatic.
It's better.
I like the dramatic ones, like the precipitation one.
The ones that make things explode
There you go. Good job. That was number one, precipitation reactions.
sometimes. Just like science, because otherwise I would not.
So the first type of chemical reaction, precipitation reactions. These are combinations of otherwise soluble ions. These get together and form an insoluble, not soluble precipitate. Yeah, no, there are two general reaction classification schemes that are out there. Decomposition belongs to one that focuses on relative arrangement of how we write out the symbols. So we talk about synthesis, decomposition, single displacement, double displacement. The downside to that classification scheme, and the reason why I don't present that one, is because it doesn't really explain why the reactions happen. And in fact, if you get into the details of it, some of the classes in that classification system don't work out very well.
Yeah.
So the idea behind this approach of organizing chemical reactions is there's an underlying explanation. And for precipitation reactions, the explanation is this. There are some ions that are so strongly attracted to each other, water can't get between them and get them apart. And so those form what we call precipitates. Combinations of otherwise soluble ions, but if you put the right ions in the same solution, they'll snap together and form an insoluble material.
That's not what we did there.
Now, we have not used a precipitation reaction in any of the labs so far. And arguably of the three types of reactions, whoops, I don't know how I did that. Of the three types of reactions, it is the least commonly occurring, certainly in terms of importance. There we go, almost there. The next two form the bulk of the types of reactions that we run into, particularly in biological systems. We don't see a lot of precipitation reactions in biological systems. The main ones would be formation of bone and teeth. If you're looking at general organisms, you talk about any sort of mollusk, shellfish, anything that makes a shell, that's going to be involving a precipitation reaction. But largely most of biological chemistry does not involve precipitation reactions. However, the other two, acid-base reactions, these involve the transfer of hydrogen ions from an acid to a base. We're taking a hydrogen ion that is poorly attached to one molecule and allowing it to form a stronger attachment to another molecule. This is the fundamental unit of positive charge. It's a naked proton. It's lost the electrons it was attached with. Something else took it, and so now it's got to float around in solution until it finds a better source of electrons. The third type of reaction, and arguably the most challenging, what we refer to as reduction oxidation reactions. Reduction oxidation reactions. These involve the transfer of the fundamental unit of negative charge, an electron. These involve the transfer of electrons from the substance being oxidized to the substance being reduced. So one thing loses electrons, another thing gains electrons. So acid-base reactions are incredibly important biologically because of these big molecules called proteins. Proteins form the major structure of organisms. They also form the major function of organisms in the form of catalysts. Specifically, we call them enzymes, molecules that accelerate other chemical reactions. Their three-dimensional shape is very subtly influenced by the presence or absence of hydrogen ions. Reduction oxidation reactions provide almost all of our chemical energy. So whether we're talking about organisms in terms of the food that we eat, we strip electrons off the food that we eat and give it to the oxygen that we breathe, or whether we're talking about a society, the methane we burn, we strip electrons from the methane that we burn to the oxygen that we combust it with. All of our energy comes from reduction oxidation reactions. So when we get back together on Thursday, we'll talk about how to write each of these three types of reactions and then tie it back into the calculations that we did today. All right, thank you all. I will see you all on Thursday.
Sounds good.